Kindly drop a comment at the comment section of the YouTube if you are on this live class with me right now. Drop your comment at the comment section of the YouTube so I can quickly recognize your presence. Thank you very much. Yes, so I can quickly recognize your presence. So we shall proceed. If you have any questions concerning this course, after this class, you can let me know. So I will definitely go through your questions, precisely speaking. And if you feel like maybe there's one slight error somewhere, you can let me know as well. So I can, work on that. Thank you very much. Okay, I received the notification that it's not clear from your end. Is it the board? Can you send a screenshot, please? Okay, if you are with me there, please kindly let me know. Still have to go back to the live. Let me see if it is clear right now what I have here. Thank you. You can use the comment section. Use the comment section of the YouTube so I can actually know if there's anything going wrong. Use the comment section, please. Very good. I've seen your response telling me you can see now. Thank you. So I will definitely proceed. Always make use of your uh, always make use of your comment section. I'll try and be checking once in a while. So thank you very much on that. While I appear, so we're going to start with the module one. Unit material, which has to do with oxidation reaction. Oxidation reaction. Exactly. That is where we are going to start from. So, um, please, if you find anything difficult, just send your message to me on WhatsApp. Is opened. I will always read your message on WhatsApp. Thank you. Okay, oxidation reaction. That is exactly where we are going to start from this morning. Now, here we go. When we're talking about oxidation reaction, there are different given reactions, definition of oxidation reaction. So we are conversant with oxidation. Oxidation, simply to say that removal of hydrogen, addition, of oxygen. That is just the simplified way of defining what we call oxidation. So, in the course of these organic synthesis, this course deeply look into what we call different oxidation processes that involve in producing various organic related compounds. Okay, so then after that, it's deeping into what we call different reactions that involve in what we call oxidation and how the process actually take place. Now, according to this given material, here oxidation simply means removal of hydrogen, addition of what? Of oxygen in a given related compound, although there is also change in oxidation number, as in the case of what we call the oil rig, which simply means oxidation is loss of electron. Oxidation is loss of electron. But if you remember the cases of increase in number, where you have something like this, 0 plus 1 plus 2 plus 3 continuously. This process here is called oxidation. Take note of that. While the process here with this arrow is called what? Reduction. Okay, reduction. So these two that you're actually seeing here explain clearly what is actually happening in a given oxidation reaction process. And with respect to that, we now begins to deepen into how oxidation reaction actually affects what we call organic synthesis. Okay, so we have it in different forms. Let me quickly deepen it into the following. Now, some examples given here include number one, successive oxidative of dehydrogenation of ethane. Yes, dehydrogenation of ethane. Now, when we're talking about dehydrogenation of ethane, dehydrogenation of ethane, okay, simply means when hydrogen is being removed from ethane itself. As you continue to remove the hydrogen from ethane, what happens? The number of hydrogen there continue to decrease, leading to formation of another unsaturated organic related compound. Now, take for example now, all those processes involving oxidation as it is used under this course is related to number one, where we have dehydrogenation of what we call ethane. Now, when we dehydrogenated ethane, ethane is being dehydrogenated to what we call ethane. Then further dehydrogenation leads to formation of what we call ethane. That's it. Okay? C2, H6, reduced to C2, H4, reduced to C2, H2, respectively. This process is oxidation reaction as a result of dehydrogenation taking place there. Hydrogen is being removed, two hydrogen removed, and eventually this is the last product that we have there. That's number one of the reactions that involve in oxidation. Okay, so here we go. Number two, where we have the degree of oxidation increase as more of a methane, which then changes from methane to methanol, from methanol to methanol, from methanol to methanoic acid. So it is not only when you remove hydrogen that oxidation reaction is taking place. Also, when you add hydrogen, that is a case whereby oxidation of methane, oxidation of methane. So in the case of the oxidation of methane, we all know that methane, okay, can change to a compound known as what we call methanol when oxygen is added. And methanol can also change to what we call methanol. Okay, methanol change to methanol, and methanol can also change to what we call methanoic acid. And eventually, methanoic acid can change to what we call CO2, which is carbon dioxide. Now, if you look at this expression that we have here on the board right now, you realize that now oxidation that is actually taking place does not involve, does not only involve in the removal of hydrogen, but as the hydrogen is being removed, what happens next? Oxygen is being added to it. Now, I'll give you this from here now to understand clearly. If you look at the structure of methane on its own, referring to what we have here, if you look at the structure of methane on its own, you realize that methane is CH4. Then methane change to what we call methanol, that is CH3OH. What do you notice here? No more CH4, now CH3OH. Hydrogen have been removed and OH have been added. Then changing to what we call methanol. Methanol is C followed by double bond O followed by H in this case. Now, this is just a simplified forms of representing what we call methanol. Now, methanol then change to what we call methanoic acid. What happened? Then we have methanoic acid as COOH. Then possibly we can have H here. Can you see that? Now, H and H, one oxygen being added to form what we call the methanoic acid. Then eventually, when you now remove the hydrogen that is present here, it eventually form what we call CO2 that we are seeing in this place. The CO2 that we are seeing here, you can see that oxygen now prevail with carbon without the presence of what? Of hydrogen in this related compound. This is another form of oxidation reaction that you can be asked to write the sequence involved. Now, I proceed. The next one that we have there include oxidation of carbon in organic compound involves in any of these following. We have other related examples apart from these two that I have mentioned here. An increase in the multiple bond order of the carbon atom. When we say multiple bond order, what does that mean? Carbon bonding together with another atomic related compound. Number two, addition of oxygen to what we call carbon atom. Carbon can react together with another oxygen, okay, such as carbon and oxygen, okay, which is the case of alkanon. Replacement of hydrogen on a carbon atom by a more electronegative element, especially oxygen. What does that mean? That simply means when we replace hydrogen with more electronegative elements such as oxygen, as the case is there. Now, that is that from there. Now, number three now is we should talk about what we call the oxidizing agents. Oxidizing agents. Now, what is oxidizing agent? Without oxidizing agent, it should be noted that we cannot talk about addition of oxygen or removal of hydrogen in a given related compound. So, when we are talking about oxidizing agents, oxidizing agents, These oxidizing agents that we have here, they are compounds, okay? They might be organic compound, they might be inorganic compound, they might be both combined organic and inorganic related compound, which have sufficient or rich in oxygen. So because they are rich in oxygen, they are capable of performing this oxidative function. Exactly, that is oxidation function. Okay, so these are what we call oxidizing agents. So among the oxidizing agents that I have here, I'll be introducing the following to you, where we have what we call chromic acid. Chromic acid is present there, which is H2Cr2O4. That is the equation for it. We have many related what we call oxidizing agents, but I would like to be taking them one after the other so you can understand the concept carefully. Now, in connection to this that we have here right now, in connection to this that we have here, which is called chromic acid. Now, there are ways that we prepare the chromic acid because you have to prepare them so that they can perform the function. Some of them you have to prepare them intimately. What does that mean? Or intermittently rather. What does that mean? It simply means once what you want to use it for is available, you can now procure them. You can't procure them when the reaction you want to use them for is not available, or else they will degenerate or depreciate and they will not be able to perform their function effectively. Now, preparation. How do we prepare this said chromic acid? They can ask you to write on preparation, equation for preparation of chromic acid. Now, here we go. Let's make this one A, our number 1A. So the preparation is done by heating what we call sodium or potassium of what we call K2 of a Cr2O7 rather, Cr2O7 with what we call H2SO4. Do you remember this orange compound, K2Cr2O7, or this one, Na2Cr2O7? So that is what we're talking about there. So when you make them to react together with what we call H2SO4, then the product that will be formed there is this one that we have in this place. And the equation for the reaction is Cr2O7 2 minus to give rise to what we call, in the presence of H2SO4, to give rise to H2Cr2O7. Then further reaction with H2O in this place, then produce this one that we have there, 2, then Cr2, sorry, O4. Now, if you look at what we have on the board, this is the equation for the preparation of the said compound. Which compound? The chromic acid, a good oxidizing agent, which have various applications. Okay, now in another form, we have what we call oxidation of primary alkanol to carboxylic acid. Take note of this. This is A Roman figure 1. So A Roman figure 2 now is what we call oxidation of primary alcohol to carboxylic acid. Oxidation of primary alcohol to carboxylic acid. Carboxylic acid. So when it comes to oxidation of primary alcohol to carboxylic acid, how is it done? And most of them is through what we call oxidation process. If you remember the case of KMNO4, K2Cr2O7, they are commonly being used here, okay, for the process of the oxidation. First of all, it changed them to alkana. From alkana, it then changed them to what we call carboxylic acid. In most of the industrial process, some of them, they don't want preparation of aldehyde, which is called the alkana, before the carboxylic acid. So, which is the subsequent substance that is compound that is being produced along the process. Now, here we go. The equation, the correct order of the equation now is that alcohol can then change to what we call aldehyde, which can then change to what we call the carboxylic acid that we have there. So all these processes that we have in this place, they are oxidation process. Likewise, this one as well, oxidation process. Now, I'm done with that. The second one that I have there, which is number 2, pyridinium chlorochromate, which is PCC. Yes, pyridinium chlorochromate, which is PCC. Now, this mentioned PCC is the next water oxidizing agent that we want to check right now. How is it being used? First of all, before we talk about the usage of PCC, we need to talk about what we call the preparation. So I've mentioned the first oxidizing agent. So the second one now is PCC, which is what the pyridinium. Yes, pyridinium chlorochromate. Yes, that is the compound, as you can see on the board. So that's number 2, just like saying, from the number 1 then to the number 2. So pyridinium chlorochromate preparation. It is the reaction between what we call the pyridine and what we call chromium trioxide. Chromium trioxide. So for the preparation, we react what we call the pyridine together with chromium trioxide. And when we do this, I believe you know the formula for this. This structure of this one here, just have our N in this place, case closed in the court of law. So that's standing in the position of our what? The pyridine. Plus what we call the chromium trioxide in this place. So our chromium trioxide, where we're going to have our O3. So eventually, if we make use of what we call conc ACL. So the compound that is going to form in this place is going to be this related compound of where we are going to have C5H5NH followed by the CrO3Cl. Yes, this is the compound of what we call the PCC. Now, this compound of PCC, of course, it has various applications. I want you to know that. So they can ask you to mention what are the applications of PCC. The applications include as a selective oxidation of alcohol to aldehyde, leading to oxidizing many related compounds. So since we said oxidizing agents are good agents for what? For changing any given related compound to what? To carbonly related compound. So PCC is useful in that case. Take for example now, when you have 2-phenylethanol, okay, may be oxidized to what we call phthalate without subsequent oxidation to phthalate acid. Now, I said something the other time. In most of the industrial process, they want to convert alcohol, they want to convert they want to convert them to what? To aldehyde. So paying to that, they want to convert them to aldehyde. But when you use some ordinary oxidizing agents, when you convert alcohol to aldehyde, it will proceed to convert it to what we call carboxylic acid. Now, we don't want the carboxylic acid, or what we actually needed does not have to, produce carboxylic acid. So what do? We now choose a selective oxidizing agent. The selective oxidizing agent will now lead to production of aldehyde without producing the subsequent carboxylic acid. Let me give you this one that is mentioned here. Conversion of 2-phenol ethanol. This is ethanol like this now. 1 and 2. Now, this is OH in this place. Put your phenol here. One and two. This is 2-phenol ethanol. Now, this 2-phenol ethanol that you have in this place, when you make use of PCC as a good oxidizing agent there, what will it produce? It will produce what we call the phenol acetaldehyde. Phenol acetaldehyde. So this is the possible structure of phenol acetaldehyde there. Just your usual benzene structure. Now, it has produced the phenol acetaldehyde in that case, but there's something I want you to know carefully. PCC is recommended in this place and not any other agents. Apart from PCC, another agent that we also have there is KMNO4 and osmium tetraoxide. Yes, KMNO4 and osmium tetraoxide. That is the next one we have to talk about in this place right now. They all have their own importance application. Different oxidizing agents have various applications. That is what we use them for. I want you to know that carefully. What specifically what we use them to produce, precisely speaking. Now we shall proceed and discuss further concerning this. Now, KMNO4 and OSO4. The symbol for osmium is OS. So osmium tetraoxide. Take note of that, okay? Now, we have applications, precisely speaking, dodging the preparation there. Now, for OSO4 or KMNO4, in aqueous base, reacts with what we call alkenes to yield what we call 1,2-diene. Now, when these mentioned here react together with alkenes, they produce what we call 1,2, which is diol rather, diol in this case. That is what they produce. Now, the reagents used to convert alkenes to corresponding diol. So, what does that mean? That means these reagents that we have in this place will determine the corresponding diol. For example, now, one typical example here is ethene. Ethene can be changed to what we call diol in the following sense. In the sense that then we are going to have C followed by H followed by OH. We are going to have CH followed by what? OH. Now, this one that we're actually seeing in this place is called ethane 1,2-diol. Coming from where? Coming from the ethene. Okay, which agent do we use there as a good oxidizing agent? We utilize KMNO4, or we make use of what we call osmium tetraoxide. Okay, now by a stereotypical process called design hydrosylation. So the process that we use to convert alkane to 1,2-diol, such as the glycol, is called the syn hydrosylation or syn addition of two OH group in a very quiet and simplified manner. It's just like when this syn hydrosylation simply means You bring two OH to join a typical given compound. That is exactly what we're talking about here. You bring two OH to join a given alkene related compound. Okay, so now in this case, the reason why we call it syn hydroxylation or syn addition is that because they involve the formation of the intermediate cyclic inorganic ester that decomposes to diol is subsequent. Okay, so there are steps involved, and there are processes that's involved in that. Now, apart from this that we have here, we also have what we call the usage of what we call osmium tetraoxide. It gives excellent yield of 1,2-diol, but it is toxic. So they can ask you, why do we prefer KMNO4, or what is the advantages of this over this? Advantages of this over this. Well, in the course of preparing this one produces ester when you make use of KMNO4. But when you make use of OSO4, that does not produce ester. However, OSO4 is a what? Is a toxic oxidative agent. Okay, it can cause what we call blindness and expensive. So the disadvantages of OSO4 is that it can lead to blindness and it is expensive. Okay, so KMNO4 is expensive and safer to use, as it gives much lower yields of that, or can you say that? So in that case, in comparison, KMNO4 gives lower yields of diol, while osmium give high yield of diol. However, the two of them are expensive. I get my point now. In the case of OSO4, that one can lead to what we call blindness as its toxic, nature. But KMNO4 does not lead to any blindness. Now, due to purple aqueous KMNO4, this reaction is often used as what we call quantitative test for presence of alkene. If you could still remember this, then the KMNO4 has its own purple color, and because of that purple color, you realize that they commonly use it to carry out various tests for some related compounds if there is presence of alkene, where we have what we call the terminal alkene and internal alkene. So in this case now, they can ask you to write tests for confirmation of the presence of alkene. What is the test? Add dilute KMNO4 plus a sample of unknown compound. Okay? Take note of that. So if you are using KMNO4 to test, dilute KMNO4, add it to unknown compound X. If the color, which is initially purple color, change to what's called gray black. So that showcases the presence of what we call the alkene compound. Okay, so the gray black is as a result of the MnO2 precipitate. So that means the KMNO4 changes to what we call MnO2 in form of precipitate. Okay, now another oxidizing agent that we also have in this place right now is called ozone. Yes, ozone as an oxidizing agent. Quick one, optional aside. Let me quickly remind you that ozone is an allotrope of oxygen. If you could still recollect, it has its own properties as well. It's commonly used in railway or subways, precisely speaking, and it occurs in the atmosphere there, which serve as what we call ozone layer, to prevent essence ultraviolet to reach the Earth's surface. It absorbs more of the ultraviolet. O3 is ozone. Being ozone, so what are the things we need to know about this ozone as a good oxidizing agent? Yes, what we need to know about it is that preparation is an allotrope of oxygen, highly reactive, okay, obtained by passing steam of O2 over a high voltage electric discharge. So when they ask you what is the alright description on preparation of ozone, what they want to hear from you is that they pass what we call the steam of O2, steam of O2 over a high voltage electric wire. So, I mean, discharge. So, when they pass it through high voltage electric discharge, then it produces subsequent, ozone. Now, what are the applications? Number one is under what we call ozonolysis, or you call it ozonolysis, depending on how you can pronounce it. Now, ozonolysis is the reaction between ozone and alkane to give unstable intermediates, okay, that decompose to an ozonide. So, ozonolysis is as a result of the reaction between what we call alkane, then plus what we call O3, then to form what we call ozonide. So it should be noted that ozonide is not just formed, but there's an intermediary before we reach this place. Alkenes reacting together with ozone to give ozonide. That is what refers to as ozonolysis. So ozonide is then reduced directly to what we call acetic acid by zinc metal. So through the process of reduction, then there is formation of another needed compound which is called acetic acid. But for this reduction to take place, we will need what we call zinc metal. Okay? So now, eventually, this acetic acid then yield what we call aldehyde or ketones. Now, under the further reaction. So there is something I want you to understand in this place carefully. What is that? That thing is that each stages of preparation of a given related compound, there is always a subsequent. For subsequents not to be formed, there are some suitable oxidizing agents which can actually perform this function without, further formation of any subsequent related compound. So that depends on what exactly did you want to produce. Now, I am done with that. We shall now move to where we have peroxy acid or acid, peroxy acid or acid. If you check your course materials, you see those mentioned there, referring to them as what we call peroxy acid or acid. And let me quickly help you with the name. Why do we call them peroxy acid or acid? Now, if you call them peroxy acid, you are right. If you call them acid, you are also right. In what sense? They are also oxidizing agents. RCO3H actually represents them. So the presence of this H in this place makes them what we call the peroxy acid. So like pa means one there, okay? Acid, one acid. So that is what it represents. If you remember the case of what we call the hydrogen peroxide, you know that hydrogen peroxide is H2O2. That's formula for hydrogen peroxide, H2O2. So the case of the peroxy acid, or you call them acid, is quite different. Now, their own general formula is this one you are seeing on the board, where R represents what we call the alkyl or any other related group. So that means we write all of them like that. Now, used for oxidation of many organic compounds, okay? What are the typical examples of this peroxy acid or acid? Take note of that. acid. We have the following as an example there. We have acetic acid. Acetic acid, okay, is given in the form of CH3, CO3H. This is acetic acid. We also have what we call benzoic acid. Benzoic acid is just like drawing the structure of benzene, you know. We have pH, which represents fairly CO3H. Now, when you draw a structure like this, take note, this is benzene ring structure. The moment it has this on it, it is no more benzene. It has become Feli. Yes, Feli. That's why there's pH there. So that simply means you're actually adding what we call CO3H in this case. That's all. So this is the formula for benzoic acid. Now, number 3 that we have there include what we call the trifluoroacetic acid, CF3 followed by CO3H. This is what we call trifluoroacetic acid. Take note of that, such as C, 1, 2, 3, F, and F, and CO3 followed by what? Followed by H. This make up what we call the trifluoroacetic acid. And the last one that I have there is the M-chloroperbenzoic acid. M-chloro has to do with what we call meta. There is meta, there is para, there is ortho. Okay, now when we are talking about ortho, meta, and para, we are actually referring to the fact that we have those related compounds in which the rotation determines their name. Now, the M-chloroperbenzoic acid is also another organic related compound on its own. Take note that this YouTube is actually recording everything you want it to record, and you can always come back to it and check this video later. So where we have M-chloroperbenzoic acid, okay. So we have MCl followed by C6H4CO3H. You see, you don't have to disturb yourself much. You'll be like, what does all this actually stand for? It's a very simplified structure that anybody can draw. This is it. When you have a compound of this type, this is your benzene automatically. Now, from there, you then attach your M for the chloro. So we have orthometa para. From here to here, make up what we call the para. And if I'm not mistaken, from here we have your ortho. This is your meta in this place. So there we have Cl being added to it. So from Cl, then what do we have next? We now have CO3 followed by the H. So this is what we refer to as M-chloro. So that means that there's tendency for orthochloro. There's tendency for what we call the parachloro, but the one that we're actually using here is called the metachloro. Okay, so M-chloroperbenzoic acid, that is another oxidizing agent that we also have there. So alongside, the short name of this one is MC followed by PBA. That is the short name for the compound. So it's not all the time I'll be mentioning the name anymore. Once I just mention MCPBA, you should know definitely this is what I'm talking about. Now, let's talk about preparation of this said compound of par-oxycarboxylic acid. That's where we are going to start from. Par-oxycarboxylic acid. How do we prepare the par-oxycarboxylic acid? And what are the applications of this mentioned related compound? Preparation of par-oxycarboxylic acid, which is also called the par acids. So they are usually prepared by the reaction of carboxylic acid with hydrogen peroxide. The reaction of carboxylic acid So when you react carboxylic acid together with H2O2, which is called the hydrogen peroxide, so the compound that will be formed is going to be what we call the par acid that is needed there. You know, typically, there are different forms of par acid. It depends on the one that you are actually preparing in this case. Now, with respect to that, there are some certain things I want you to know. It is the compound that you're actually preparing of acid, you're actually preparing that will determine what's it called? That will actually determine the product that will be formed. Take for example now, I'm using H3C followed by C double bond OOH. Of course, this is acetic acid. Acetic acid is another name for ethanoic acid. So when these react together with what we call H2O2, then it produces the respective per-acid. And the per-acid I'm preparing is per-acetic acid. So now here we are going to have H3C, C followed by double bond O followed by OH, then plus what? H2O. Now, there's something that is not there's something about this course itself that it is logical. What is the logic there? The logic there is that this one that you are seeing is stand on its own. If you remember where I made mention of the per acid or peroxy acid, I made mention of a particular member, the per-acetic acid. You see that per-acetic acid is CH3, CO3 followed by H. So in order to get per-acetic acid, you must obtain it from where? From the acetic acid itself. That is it. You must obtain it from per-acetic acid itself. As simple as that. So what do we want to do? We just want to add oxygen to it. That's all. So on adding oxygen to it, it's quite simple to say H2O2 reduces to what? H2O. One oxygen is missing. Where can we find it? We can find it here. From CO2H, it has become CO3H. Simple. That's the logic behind it. Now, in this case, they are mainly unstable and generally have to be prepared freshly before use. Yes, that's the problem. They are not stable. So they can ask you advantages of this over the other, or preparation of per-acetic acid. So when they ask you what are the advantages of this over the other, you should know exactly the information to give about them. So mainly unstable and generally have to be prepared freshly, before they can be used. Now, in connection to that, however, we have other related compounds such as performic acid. Okay, the performic acid and peracetic acid, for example, are often prepared in situ okay, and not isolated by an action of H2O2 on the what? On the COOH. Now, these are the related mentioned, reactions that occur there. Now, let's talk about these applications. What are the applications of this paracetic acid? Where I'll be stopping for today's class. Number one is that oxidation of alkane. Oxidation of alkane. Oxidation of alkanes rather. For oxidations of alkane, which give rise to what we call epoxide. In this place, we make use of what we call N-chloroperbenzoic acid as an excellent reagent for the epoxidation of alkane. So, oxidation of alkane with the use of what we call the MCPBA that I mentioned the other time, MCPBA that I mentioned the other time, is a excellent oxidizing agent that you can use there and convert a given alkane to a respective needed compound. So that respective needed compound is actually the process refers to as what? Epoxidation. The process is called epoxidation. So what are we actually preparing here? We're actually preparing the epoxide. Take note of that. At suitable, conditions. Number two that I have here now is what we call oxidation of ketones. Okay, oxidation of ketones. Here, ketones are converted into esters or lactose. When we say conversion of ketones to esters or lactose, of course, mostly the prepared per acid are commonly used here to convert any given related compound into another needed compound. I believe you know what I mean by the lactones and the esters. The esters are those with what? With the RCO. Exactly. RC yes, the alkaloids. Okay, and when it comes to the lactone, another name for the lactone are the what? The esters, as in the alkaloids, which also refers to as what? The ketones. Okay, now next class we are going to be talking about, which is unit 2, we are going to be talking about transformation of alkane to epoxide or an carbolic compound. So the assignment that I have for you right now is that you will go and work on epoxidations and know those the structure of epoxide itself, how they typically looks like. Okay, we have different epoxide. Take note of that. So you take note of the structure, the position of the carbon, the position of the oxygen in such given related compound. That is what you are going to do for me. We've come to the end of the class for today. You can check your WhatsApp section. If you have any question, just drop the question to me, then let me know. And you need to give comments concerning the class. I want to know concerning the media related clarity, voice or vocality, volumes, and other related to. Thank you very much.